We're going to show here and demonstrate how we have been collaborative in the sense that I sort of teed up this morning. As we collaborate, as we see this convergence, this group personifies that. So my guys are going to tee this up a little bit with some slides and spend just a short amount of time showing some things that have actually been done. So a couple of the folks that I mean, you're here when we were first there this morning. So Said, raise your hand. Said Korich over here. Ahmed, raise your hand. Taha from my team here as well. So they're my guys, and we also have Prasad from Simulia down there at the far end. We have Greg Clifford from Cray. We have Steve Feldman from CD Adapco. We have Lane Lewis here as well from ANSYS. So the work we've done has been rather fun and spectacular here by having a collaboration model that works, but is relatively new. So we will share that with you. The objective really is how do we work with commercial ISVs? There are some of you in the room that work with your proprietary codes and everything's kind of under a wrap, and we can do those and control the code and so forth and so on. What we want to talk about here today with this panel is how do we do that with commercial vendors in a way that does not violate the IP? So we'll share that issue. Said, why don't you come on up if you're going to kick this up. So I challenge you in the audience, can you pick up the common themes that are here? Can you pick up the convergent themes, et cetera, et cetera? So let's listen to exactly what happened here. Then we'll be very interactive here. ISVs will have a chance to talk about what they have done and how they're doing some things. I know after yesterday, some of you in the audience have some good questions here as well. So this will be the time to do it. So we'll do this until noon lunch.
Thanks, Merle. So I think suggestion for you, Merle, I think that talk from Lynn should be yesterday before the barbecue. You know, now everybody's talking about food, you know, so we are in an inconvenient position here.
So deal with it.
Yeah. Anyhow, yeah, I'm Said Korich. I'm a technical program manager of the private sector program that Merle leads. I'm also affiliated with the mechanical science engineering department here at University of Illinois. I'm going to be just briefly, very briefly mention a few of these things that we were talking with ISVs, and it's been a pleasure working on those things. So for you guys who were here last year or a year before, you know, remember there was a big breakthrough with explicit finite element code LXDyna. There were 4 ingredients there, 4 ingredients for success in this recipe. That was Cray being a hardware actually vendor, and then LSTC, which was the company who wrote the code, and 2 of our partners, you know, Rolls-Royce and P&G. Of course, NCSA was an integral part of all of this. So again, those 4 ingredients, you know, are very important with this kind of success stories. And once we broke with 15,000 cores, I think Tom Lang was finally convinced. You know, it's hard to convince him. You know, so he was convinced that these FEA codes can scale so wide. And then we move on. Actually, I move on and with my collaboration with IBM Watson and Barcelona Supercomputing Center. You know, WSMP and WSMP Accelerated. Where NVIDIA was involved as well. You know, we port this very capable direct sparse solvers actually to Blue Waters, and we extracted some implicit matrices from implicit finite element code, and this particular solver was actually able to scale as wide as 60,000 on CPUs, and then on 512 KX7 nodes GPU accelerated. And of course, yes, last year, you know, we mentioned this story of Alia, which is a special multi-physics FEA code that scaled to 100,000 cores. Now we are involved, this is involving story, work in progress with Abacus over CLE and Gemini, you know, so Abacus for the first time is actually able to run over the powerful Gemini interconnect on Cray and Simulia and Cray and NCSA and company that resorts to be under NDA. You know, we are working with them. So I'm going to briefly show this, what it means. So this is work in progress. You can see Abacus so far has been run over CCM only. So CCM is cluster compatibility mode. And Greg can correct me if I'm wrong. I think what Cray does there, actually, it's emulating some kind of IB interconnect. Well, turn out actually that these new bundled MPIs with Abacus, like Intel MPI, Platform MPI, they are now becoming actually understanding Cray MPI. So we use the advantage of that. You can see if you are running Abacus over, let's say, Platform MPI, but under API run, which means under a Cray Linux environment, and you are actually going over Gemini, you can see the difference. For the originally colleagues at Cray, they said, you know, you're going to get 5%, which is really true, 5% for standard 5 million degrees of freedom problem. But once we start actually going to a larger problem from our industrial problem, which is 11 million degrees of freedom, we can see as much as 30% improvement over CCM. And why is that happening? Communication becomes more important than computation. That's the lecture we always learn from engineering codes. And that's where Gemini actually makes difference. And briefly, evaluation of the direct solvers in geophysics. So Merle mentioned this, you know, all of these things look the same when you look at some kind of numerical analysis. So actually, turn out that this oil exploration with the inversion processes, they also solve big system of sparse linear equations. They are complex, they are ill-conditioned, perfect for direct solver. So actually, colleagues from Barcelona Supercomputing Center, they provided a few of these matrices from their partner, which is Repsol. And we were able to see actually the WSMP did very good job, even better than standard solid mechanics. You know, we reached, for example, here almost 100 teraflops, you know, and it's scaling also to 64,000 cores with this problem. And finally, the project with NVIDIA and NCSA and IBM Watson. So we ported actually this WSMP, this very potent solver to GPUs, and you can see that on the relevant scale here, which is up to, let's say, 128 nodes, we saw pretty good scaling between CPU only and GPU version. And then you can see that actually asymptotically approaching the CPU only version. And we know why is that happening. Because right now there is a work imbalance between larger block size that are sent to GPUs. But we know also how to resolve it, and we are working on that. So again, you know, this is, if you are thinking about direct solver being a heart of every implicit finite element method, this also can give us a hope that we're going to see very wide scaling with GPU accelerated solvers with FEA in the future too. I think that will be my last one. Next one is my dear colleague, CFD guru, Dr. Ahmed Taha.
My name is Ahmed Taha. I'm the CFD lead for the private sector program. And I will add to what Syed said by presenting two elements. The first element, which is the collaboration. What does collaboration mean actually? And for us to value the achievements that we did, we have to value the collaboration that we had with both the ISVs for the software and as well for the hardware. Without this collaboration, close collaboration between us as the data center and between the software companies that we work with and the hardware, which is currently Cray, the owner of the Blue Waters, we would have not been able to reach what we did, whether with the finite element with Syed or the CFD with myself. So what I'm planning to present to you is what are these collaboration entities that I myself in the CFD part did work with during the last year. We have four main elements in the collaboration. Ourselves and you as industrial partners, in addition to the software vendors, and in this case, I collaborated with both ANSYS and CD Adapco. And with the hardware, I had help from or collaborated from both Cray, the owner of the Blue Water, Dell, Intel, and NVIDIA. And having all of these entities working together allowed us to do what we did. Before showing you the graphs, the new graphs that I got since last year, because in the same place, in the same annual meeting last year, I showed you the scaling of Fluent, which at the time was 20,000 cores, which was at the time the biggest that we scaled the Fluent. I think it was the biggest as well worldwide. We scaled that in October 2014, even more than that, which I will show you. And as well, it was our first time during this year from May 2014 to May 2015 to scale CD ADAPCO as well, and this is a big number. I will show it to you. But before showing you the two graphs, I will show you 6 elements of collaboration. What does it mean, actually, collaboration? Without having special licenses from both ANSYS and STAR, we would have not been able to run all of this massive simulation and benchmarks. ANSYS, for example, gave us a license key, which is 100,000 seats for 1 year, which is our rate it's worth of $10 million with our academic rate. This is for a full year. And with the industrial rate, you can multiply it by even, I think, 4 or 5 times. And this has been given to us as a complementary to run the scaling. STAR did the same with the power on demand. It's open-ended power on demand hours that once we'll finish the first key, we'll give the second key, which they did. So without that, we would have not been able to do it. And the second one, which is the data input itself. In order to scale the two codes to the biggest that could happen, we have to have an excessively big data input to scale. The small ones cannot scale to big counts. And we agreed that we will need to have 4 criteria in the cases that we run in order for you as users on the ground to connect and to link to our scaling. We have to have these scaling or benchmark cases representing real-life applications, and as well a big mesh, it's not a small mesh, and as well very sophisticated physics and the geometry as well, that you can feel these geometry are not just simple, that does not connect with your applications, and the physics as well. You will feel the connection between what we scaled and what you run on the ground. And by that, I received two meshes from STAR with starting from 100 million, and when we scaled the 100 million, the track 100 million for ANSYS to 10,000, they sent the one of the biggest they have, which is 830 million cells for the gas combustor, which I showed you last year, and I showed that in details yesterday in our partners. ADAPCO sent me 3 sizes, starting with the 105 for the racing car. Lehman's racing car, starting with the 105 millions, and I scaled it in February this year to 13,000. They sent 5 times the bigger, which is a 514, which I scaled just in March on the same next month to 20,000. They sent 1 billion cells, which I scaled, and I will present the number to you in few slides. Without these inputs, we would have not been able to reach this maximum. The third area for the collaboration, which is the technical support for the pre-processing and initialization. Without our own computational resources that we have here in the Blue Water and the NCSA, this work would have not been brought to reality. And there was a big challenge for fitting this huge mesh for the pre-processing, for the meshing the case, especially with ANSYS. ANSYS sent 6 pieces for the mesh, and I have to stitch it. I have to bring one single mesh for the 800 and the 30. And without having a node which is from the Intel, and this is why we have Intel as one of the collaborators, a node which is 1.5 terabyte of memory. Without this node, I would have not been able to create or to stitch this big mesh for the 830 million. And it consumed 576 gigabyte of memory out of the 1.5. And the pre-processing for such a case took around 1.5 hours just to read the case with the help of the technical engineers from ANSYS. The same was with the ADAPCO as well. FTP, the 1 billion cell and pre-process it and getting ready to run, it took around 6 hours, 45 minutes just to transfer the file, then to open it on the big server, just for the issue of the pre-processing. The fourth area for the collaboration, which is the tweaks that both ANSYS, ADAPCO, and the CRAE engineers has to do in the MPI ranks in order to enhancements for the MPI itself to be able to spawn this huge amount of cells over the massive amount of counts. The regular MPI ranks inside the installations will not be able to do it. So a lot of work has been done with the two companies and with CRAE to make these adjustments. The fifth area, which is the special flags that has to be added to the launching command in order to optimize the codes, both Fluent and Star, so we will be able to run the code. Without these flags, I used to have errors until their engineers got involved and resolved that. 6 is ours, which is the Blue Water. Without the Blue Water and the support as well I had from the Blue Water team at NCSA, these results would have not been able to brought into reality. What did we achieve? ANSYS Fluent, we scaled it to 36,000 in October 2014. And the newest, which is just yesterday at 1 a.m. yesterday, Star scaled to 59-something cores, thousands, which is around 60,000 cores. And these are the graphs. Very good. This is the ANSYS Fluent, which is a gas combustor, typical gas combustor configuration, this configuration. And this is the curve. And you can see the scaling to 35,800. And you can see the dividing the 30 over the 35 can give you the 80% efficiency, scaling efficiency for 86% scaling efficiency for Fluent, which is a very good efficiency to have for the code. And by the way, this is for the beta version of Fluent. I'm sure that the current version, which is 16.0, then the 16.1 will scale more than that. But we did not continue the project since October 2014. If I will scale Fluent now with the 16.1, I'm sure that this will pump up more than that. So I'm just making this disclaimer. This is not the end for Fluent. And I'm sure if we continue that, this will pump up. Now, for Star, this is the newest results, which just happened yesterday, 60,000 for the racing car, Lemons racing car. And the scaling is amazing. It's 93.6 scaling efficiency. And you can see the curve that it's continuing. And because of that, actually, because of the potential for the scaling, I have 2 jobs right now in the queue in the Blue Waters. One of them is 71,000, and the other one is 6 digits, 102,000. I might update you before the end of the meeting about pumping up over that. Thank you so much.
So how do you make a guy like Ahmed happy? You just witnessed it. Let's keep the story going. Lane, let's begin with you. We've been working with ANSYS for a while. We've had several iterations, a few other things, a few challenges. You know, where do we get the input decks, whatever else. Why don't you just tell us a little of your story here?
Sure. We really appreciate the collaboration with NCSA. We don't have ready access to 100,000 cores to be able to test this, right? So we need a partner like NCSA to be able to test our codes to this level of extreme scaling. And Ahmed shared a few of the things that come out of that. There's tweaks we make because of the results we get when the simulations are run. But one of the great side benefits for us too has been there's a relatively few number of customers that are really demanding this extreme scaling. But what our focus on this extreme scaling has done has enabled us to be much more efficient at our partitioning so that even in the much smaller models with much fewer cells than what you just saw up here, we're partitioning so that even at 100 cores, you're getting really great acceleration. And that was kind of a side benefit of this focus on the extreme scaling, is that it made our scaling, even at the low end, much better. So the message is, through this partnership, through the collaboration, our code has gotten better for all levels of simulation, the small all the way up to the very extreme. And we appreciate that.
So Lane, are you saying that only when you ran the extreme did you break things that might not have broken at the small level?
That's right. And that's when we broke things, and it also forced us to get more efficient at this partitioning. How do you take advantage of more and more cores so that even at the small level there was the benefit then?
Laptops to petaflops, right?
That's right. Or not even laptops, tablets, right? Tablets and phones, right?
All right. So everybody in this room benefits, is what you're saying?
Yes.
Okay. All right. Steve.
So, first of all, I want to thank Ahmed for staying up till 1 a.m. in the morning to get the number. But again, there are very few places like this around in the world. It's not the only place, but the number where you can work with people like this on very large numbers of cores. It's a very small select group. We work here, and we work here with American customers, but we also work in Europe with a kind of similar organization and do similar things and getting similar numbers, which is a good check on both sides. But I mean, for us, this is extreme today, but in the past, what's been extreme eventually becomes the norm. It's a good sanity check on our overall direction to make sure that we're not going off in directions that are going to prevent this kind of really large scaling. And just as Lane said, it helps us with our everything we do to improve here helps us improve all up and down the whole spectrum. And I guess the last thing I would say is that there's no big breakthrough. There's just a lot of hard work. You find a bottleneck and you fix it, and you find a bottleneck and you fix it, and it's not like we rewrote the code to make it do this, but it just forces you to really concentrate on every little piece along the way and optimize it, and that's what it takes.
So Steve, if I have my story straight, in the history of Star CCM, you've actually had two versions. Didn't you actually sort of keep a legacy code going, but then you also brought a newer one in the last, 6-7 years, something like that?
Star CCM Plus is our newest code.
Okay.
Star CD is a legacy code, which is still available and used for certain niche applications where the physics haven't quite gotten into Star CCM Plus yet.
But you took the business choice to not rewrite, or is that a fair representation of what you did with CCM Plus? To rewrite, or did you start from scratch?
It was a completely blank piece of paper. We started from scratch, and
wow,
and that's what we did.
Okay. So a good example of a conscious choice to take advantage of parallel platforms to run the code even better. Good. We'll wait for more news 1 o'clock tomorrow in the morning. See what we can find out there. So, Prasad, how does this affect your organization and your opportunity?
Basically when we talk to our customers, basically we kind of understand it in this way. They give us the message that solve our workflows. Okay. So that's what they say. So we go ahead and do that. And then once they solve, and then they say, okay, all right, give us reliable and accurate results. And so we do that. And basically, so we put emphasis on that being a part of our DNA from the start. And now that you solve a problem, now make it faster. I can't wait for 2 days, 3 days, 4 days, 5 days. I want it now. So that's what the message we're getting from our customers now. So that's what we're focusing on, and we're reaching out to NCSA and to basically gain the knowledge that's already out there, complement what we have in-house. And the hardware part is always very important. and external validation is something that's also, you can kind of tweak your problems in certain ways so you can get performance and showcase problems and so on. But really having an external party doing the validation and putting out the numbers out there kind of holds your feet to the fire. And so we're very happy to be in this partnership with the NCSA.
Prasad, thank you on that. Also, thank you for being a University of Illinois alum, coming back and being here on the campus. Just for grins, raise your hand in the audience if you're a U of I alum.
Not in the audience. But yeah.
Look at this, all three of you guys. It's a good day. It's a good day. So, Greg, you've been with us all along here, and I do want to state that as much as we had worked with some scaling and performance, and we're proud of what iForge does, and in fact it does a lot, and it's really powerful, there are some things that can only be done on the larger machines. So because we've had access to Blue Waters, we built the thing and we built it in some ways. Can you share with us what your observations have been? You are in charge of working with industry and particularly manufacturing at Cray. So how have we helped you? What sort of observations have you gained from this last couple of years?
Well, of course, Cray is focused on the high end, to a large degree, and this collaboration between industry, the ISVs, and NCSA has really been powerful to as you've shown, you really push the high end. I guess the private sector program in particular, one of the things I really appreciate about it is bringing in industrial customers, and obviously the ISVs provide code expertise and the applications that can be demonstrated. Cray working with NCSA has this HPC focus and supplying the high-end resources, but the customer and the user community having the model is of course a key thing because those real-world models are vital. The other thing I'd like to point out that I think is really critical to all of this is it's that user community that really brings the business case to all of this, and being able to show that it's nice to be able to scale up and demonstrate the science or the computer science aspect of it, but you have to have that business justification for doing the work in the first place, and being able to show that if we can run at this scale and this level of performance, that allows us to do this class of problems that has the following return on investment to our company and to the industry as a whole. And that's really vital to kind of justify the whole process, I feel.
So Lane, let me ask you, how do we keep this from just being a stunt?
I think we have a real opportunity to continue, building on Greg's point, what's possible today that wasn't possible to simulate only a couple of years ago. And I guess a challenge I would throw out there is bring on your big designs, but not just bring on your big designs, but why don't we see a more systematic parametric design approach? Because it's possible now, and I really want to encourage that. It'll produce more robust designs. It enables testing of many, many more different permutations of a design than you could ever prototype. And it's feasible now to do that. And so that's a challenge, right? Is more parametric, robust type of design with this capability now.
So Steve, I think you were saying, we try this, we iterate, break something, fix it, find another bottleneck. What does this do to your process? Lane, you just alluded to it, but Steve, why don't you add to that a little bit? What do we know about the process of dealing at some scale and actually working with codes, and what do we not know? And what has this helped you learn?
Well, when you build a code, you make certain assumptions about the kinds of problems you're going to solve. And they work for a while. And then all of a sudden you find out that either people aren't doing what you really expect them to do, or they're doing it at a much larger scale than you really had in mind when you started the program out. So we've had to go through several revisions in the code, particularly with the way we decompose things, because what the problems that people were trying to do just didn't fit into our original assumptions, and it was it's a lot of work to go back and take things that are basically working, but refine them to work on much larger scales.
Can I answer?
Yes, go ahead.
I was thinking another, real vision for ANSYS is the multi-physics aspect, right? And that adds a whole nother dimension of challenges. Today we're seeing, the mechanical benchmarks, the fluids benchmarks, and starting to tackle some of these multi-physics problems. That's the next level of challenge we really have to get the scaling in a multi-physics domain, and that's something that ANSYS is very much focused on, is to enable a full system product simulation, is being able to couple all the physics together, the electrical, the mechanical, the fluids, embedded software, and we still have work to do there. But that's really the next challenge too.
So one obvious question seems to be the chicken or the egg problem here. Is there demand for this sort of scale, or is there not? Did you just ignore this all these years because there wasn't demand, or was it because you had no access? So Prasad, if you just describe a little bit, what have you seen with demand? How's demand changed in the past years for you guys?
I think, basically more and more, like, other panelists have mentioned, more realistic modeling is basically, there's more and more demand for it, less and less assumptions basically being made in the modeling, and thereby building bigger and bigger problems, bringing in multi-physics, multiple expertises in there, and so on. So all this is being aided by availability of computing power, and so we have to, as a software developer, vendors, we are basically having to adapt to this, and it is for real. Our customers are demanding that they solve more realistic problems and solve them faster. So I think this we sense that, and we are basically adapting to the trends.
Just to follow up on that, at Cray, we obviously have some very high-end customers. Blue Waters is a great case, but you do find yourself wondering, does this demand that you see at the national laboratories and some of the research centers, does that really apply in industry? And one of the things that I've seen, trying to look for how Cray products fit into the commercial marketplace right now, is I've just been amazed at, the petascale problems that exist in commercial companies. And it's not just the extreme high end; it's across the board. So, and it's clear to me that a small group of people in commercial companies can easily suck up a petaflop of compute power right now. Going into things like stochastics, running up the larger size of the models, coupling together what's happening in the manufacturing floor with the in the simulation and so on. So there's no question that there is a real demand for scaling to hundreds of thousands of cores on a daily in a production process.
My only thing to say to that is bring it on.
Yeah.
Yeah, absolutely. But what is it, the stochastic piece to this that you're seeing that has changed that demand, the petaflops, petascale sort of nature, what else has changed? And we'll let the audience maybe answer some of this too. Is the demand for better physics just different than it used to be? Do we have more digital insight than we had yesterday? A few other things. I have a comment from the floor because this guy has my cell phone number and texted me. So the comment was, this ISV legacy problem that we've had has been in the way at NCSA since day one. Okay, so this first clue, the guy's been here since day one, right? Used to be they couldn't deal with the parallel and had no economic incentive. Now this guy was successful because he wrote his own code and he had to parallelize it. So what's the learning curve like? is the demand for more physics, or is just the demand for more stochastic? What does this look like? What are the components here that we need to keep in mind as to why we're here today with a different story than we were 2 years ago? Any of you?
Carl, if I can say some, so I have a few hats here, one is academic, obviously, so when you're looking at, for example, multi-scale methods, people have done a pretty good job in multi-scale methods, but multi-scale methods can go as far as they can go, so if we can, instead of multi-scale methods, actually apply some kind of DNS approach, actually trying to resolve all those things, on a single domain, you can easily get to this point, where you're going to be scaling on 100,000 cores, you're still not going to be happy, and I like to say what Professor Hughes has said, supercomputers engineering, he said in 2003, they will be size of the football field, but we won't be able to solve, we'll be still scratching on the surface for some problems, and that's definitely the case. If you guys remember last year, I presented the case of human heart when we were actually looking at the some of these details, even on a fiber level, and coupling the fluid flow with solids and with also the electrical propagation through the heart, and we scaled on 100,000 cores. Such as, to give you an example, if you had an imaginary system, with one core and so much memory, it will take 18 years, actually, what we have done under the 2 hours, on Blue Waters.
So I think I'm hearing you say that there are better methods than there used to be. So maybe that is a maturity factor here of HPC and parallelization. I think I heard somebody just yesterday, and gosh, Joe, maybe it was you from Intel, said that we've really been doing parallel computing for 11 years. That's it, even though NCSA's been here forever. So Steve, you were about to say something there as well.
Well, I think the things that are going on is, first of all, at least among the big companies, nobody questions anymore, very few people question anymore that simulation is the way to go. Whereas years ago, not everyone was convinced. Secondly, now that they really are into simulation, they want to do it well. And doing it well means in many cases, doing it large. You need to be large enough so that you don't have phony boundary conditions impacting your analysis. You need to go back away from what you're interested in to the real boundary conditions. So people are building larger things. And it ties in with what Lane said as well. People are trying to do multi-physics. It's the next big push, and it's a hard thing to do. It's a hard thing to do in a lot of companies because they're not well organized yet. They have their separate independent departments, and they don't really want to work together that well yet. But it's coming. And the last thing, which is driving all of this, is not necessarily, I think, that everybody needs to do 60,000 core analyses, but if you're trying to do design space exploration, you can't afford to do 160,000 core analyses, but you might take up 60,000 core at a time, doing 100 analyses all at the same time in order to get your job out quicker. And when you do those kinds of things, that's an embarrassingly parallel system. All of those things scale perfectly because they're completely independent. So all of those things are driving people towards more and more analysis.
Mm-hmm. Very, very interesting point. But you also used the word that's now the trigger for, I know what the audience is going to ask about, and that's the affordability. So we had this conversation last week, so this is no surprise for these guys. So I mean, you've long been accused of having a linear approach to licensing, which means we get to this 60,000 core thing and nobody can afford it, so why even bother? So I want you to have the first response to that question here before we throw this out. And what does this do to change your own business models? What do you love these guys out here or not who actually want to run at 100,000 cores? And I want to go on record saying that we do love these guys because what I hear from the folks in the audience is we need every commercial code that we have here to be better. This group cannot live without the commercial code base. So they love you, sort of, until the licensing gets in there. So let's address that. Lane, start with you.
Right. So I think, and building on the last question too, is it's taken real work. I mean, part of the reason we've gotten to the point today where we're doing this simulation is it required real work in the software to do this parallelization, et cetera. And because it takes real work, it's real software engineers, a investment from the company to realize these kinds of scaling and scaling efficiencies. In defense, I don't want to be too defensive, but in defense of the question, the one thing I can point to in our price book that's actually gone down over the years, it is the HPCs. So there's an economy there as well. So the cost of HPCs only a couple of years ago is significantly less today than it was only a couple of years ago. So there's an economy that's captured there too. But the reality is, the work isn't done either, as has been pointed out here by a few folks. The continual hardware advances, we made a major investment to take advantage of the GPUs and a little bit of a collaboration with NVIDIA to do that. And again, it's real work, but now the GPU is another core to us that we can take advantage of, but requires this investment and this work to do it. And I would say in one last defense, and on the flip side, this ties into GE's industrial internet a little bit too, and the power of 1%, and this notion of doing this robust, systematic, parametric design. I mean, there's real return there too. If I think this is a Jeff Immelt quote, if the jet engine is 1% more efficient, it saves the airline industry $2 billion a year in fuel costs. I mean, that's a real huge savings, right? And it's only in the investment to enable the scaling and the code on our side that enables GE to then return those kinds of cost savings to their customers as well. So it's a large ecosystem, and hopefully we both and all benefit from that.
So Prasad, I want you to go next because it's been probably 4 years ago I heard some of your guys say that 90% of your code base is running at 8 cores or less. So this ought to be well, maybe to these guys, a scary thing. If you take the 8-core license and you take it to 80,000 cores or wherever you end up, what does that do? And our heads don't quite compute that. So how do you address that?
We want our customers to use all the hardware that they can get their hands on, and that's what. And our pricing model takes that into account. And certainly, the return in terms of there is such a thing called efficiency. So if you use more cores, not necessarily performance is going to go linearly up. So we account for that as well. So the cost of software is basically, as you increase the number of cores, your cost is not going to increase linearly as well. So it is all factored into it. And just to echo the point of our panelists in terms of the work involved in getting parallelly, performance from the code, we have about anywhere about 200 man-years of effort that has gone into the Abacus code. That would be my estimation. That would probably be more than that. But for us to, over the last several years, to make it parallel is basically is a significant investment to refactor all that code that has been generated over 200 man-years of effort. So it's a significant, and I think we basically price the model to take into account the efficiency of our code and the number of cores you use, and that's what. And we like your feedback on that.
Steve, how have you handled this?
So we really like to talk about licensing.
That's why you came, right?
That's why I came. We have a number of different licensing models, but the ones that really apply here are, we have something called Power Session, where it's a seat and it's one analysis, but we don't count cores. You run it on 20 cores, you run it on 200,000, it's the same price. There's no difference. We have a second licensing model called Power on Demand, where you simply buy hours, and these hours are they're wall time hours. So if a job runs an hour on 10 processors or it runs on 100,000 processors, it's an hour and you pay for an hour, and that's all it is. So we've really cut the cord completely between the cost of running multiple cores and the cost of running our program. And we also have, we have other licensing models as well. We have one that's geared really towards optimization, or what I call design space exploration, where you can buy tokens, and if you buy 100 tokens, you can run one job with 100 processes, or you can run 100 jobs with one process, and any combination you want in between. So when you're running optimization, you're typically running lots of jobs with not so many cores with each one. They're usually not that big, but if you need 100 tokens or you need 1,000 tokens, whatever it is to run your mix of jobs, we're very flexible that way. We've been hearing this for a long time, that there's this connection between the software getting more expensive as the number of cores goes up, and with us, it's just not true.
Greg?
Just another comment along these lines. I mean, as was discussed, not every problem needs 100,000 cores, and a lot of the users are running just on their laptop. But, I think part of what we want to talk about is what, Blue Waters and high-end systems deliver is not just high-performance computing, but high-value simulations. And these jobs that run using thousands of cores, I like to think those are the jobs that really have the most return to the organization as well. And I guess coming back to the private sector program, part of what we want to do is demonstrate the technology, but I think an integral part of this is, we want to show that, with this much compute power, you can do this class of problem that has that return on the organization. And really what we're doing is providing the ammo to the user community that, okay, here's the value you're going to get. Here's what it's going to take resource-wise, but here's the value you're going to get from it. And just do the return on investment calculation, and maybe it's not worth it. But that's part of what we're trying to demonstrate in all this is do that first case so you can actually do the math and figure out what is the value.
So this came up a little bit yesterday in our partner-only meeting, that the behavioral piece that you're now describing, call it a high-value run of some sort, but the stochastic piece, and Steve, you just brought this up. So there is some discovery. It's something we might do at a high level, high-value level, but then there is the optimization side, and running that, and you're sort of alluding to that. You've got a different licensing model for that than you do the first discovery run, if I heard you right. So it's not just the scale, it's the behavior that we want to drive in this way. So capacity computing actually matters if we want to do a lot of these. So let me throw this to the audience. We've now had some response here to we're not linear, we're not linear, we're not linear. Things have changed, but what do you want to ask from the audience? Microphones are close. We've got a hand right up here front left, and then we know Tom's got another hand.
How are y'all doing?
Good.
So I'm Wes Rhodes from IBM. I don't have anything to do with licensing, or say that. I'll save myself a lot of grief. But what I do is represent maybe a non-traditional view of where HPC can go. So what I want to do is frame a business problem for a moment, proffer an idea for that, and then just see what your reaction is. So today we're moving more and more services to the cloud. So those are larger and larger consolidated complexes. We have all kinds of privacy issues. So as we put data centers in other countries, we're having difficulty moving that data across their country boundary in order to get the insight from it. And we're looking at how to deliver things faster. So we're working on all kinds of technologies to not move the data, so leave data in place, to get insight from the data, let it represent the detailed data in a good enough level of fidelity. So what that's doing is driving more and more and more the problem set from a super big data, gee, I'm ingesting a lot of data, to one where I'm having a lot of compute, throwing analytics against the data to set up models so that I can react more quickly. So when I think of high-performance computing, I think of it for super complex, compute-intensive applications. And my suggestion is that perhaps what this technology is driving to is to that state, getting more and more complex as I have the Internet of Things just really flowing in with all this data and the interactions, by taking out some of the restrictions on getting an answer from that data, a response, so that I can meet my window of opportunity, I'm driving it into very heavy compute-based models. So maybe what I'm discussing maybe isn't why you're here today and why you've had success from before till now, but if we come here 5 or 6 years from now, that may be the type of situation you're talking about of why you're having much more success. So driving software to run into an HPC way to drive massive compute for massive insight for very narrow, micro simulations and so forth, so we can meet these commercial problems that we have for these large as a service applications. So my question to you is, given that scenario, do you just disagree with that violently, or does that sound like it's something that you see as a possibility? If so, what's your reaction?
I don't know what he's talking about.
So Wes, if I'm hearing you right, and put it in real short terms, I'm thinking you said we may use HPC in the future in ways we can't even imagine today, and that suggests that maybe this is not a zero-sum game when it comes to the usage models, and in fact we can grow the pie in a lot of ways.
I think it will take off in ways that you haven't even begun to think of it as a specialty computing. It'll be much more of an applicability for general computing.
So if you're the optimist in the room, panel, is he crazy?
No, you're not crazy. No, and I don't know if this addresses it directly, but I think you're right. The models, the use models, the business models need to constantly evolve. And preempting an announcement we're having tomorrow, it's an offering with Amazon Web Services, and it addresses all kinds of customers, right from the big monster problems to small problems to the Joe in a garage starting a business that doesn't have access to compute powers or the software and just wants to get everything in the cloud. And so we are constantly questioning, what's the next model? What do we need to evolve the model to address the emerging problems, and what are the emerging problems, which keep changing too? Some of what this, again, extreme scaling has done is it's an enabled simulation, and as Steve said, it's convinced customers that weren't sure about simulation that they absolutely need it now, and it's feasible, and you get access to it, and so all those things keep evolving.
So I wanted to address this question. First of all, just a comment. Brilliant. This panel is a brilliant. For those that can't calibrate or don't know, we had a software summit in this room, I want to say 5-6 years ago. We didn't even get you all here. We certainly couldn't even have the conversation between the academics, the hardware, and the software providers, even two competitors, about scaling and about the business model. I mean, I'm not saying we have the business model solved, but you know what? We'll work that out. The money will be there. But I just wanted to say, fabulous. All right, the fact that you all worked to get the scaling that you got, which at least from Procter & Gamble's perspective is necessary, a major issue, and everybody else you're pushing the boundary. It will flow down. The comments that you guys made, it's just an extraordinary thing to sit and listen to. And if I could applaud, I'd be applauding. I mean, it was, and for those in the room that don't know this journey, this was a long way away, right? I think we have to keep on the scaling problems, and the industry and the business. We need to be bringing our problems to them that we can't do. We need to have the imagination to make sure that we think about problems in billion element contexts, not in 10,000 element contexts. We need to be thinking about stochastics, optimization, multi-physics, all at the same time. We need to be predicting injury in a car crash, not just whether a dummy's G-force exceeds some limit. We need to predict hematoma and fracture. We need to predict human response to, I'm just really excited about it. I think the business model is still something we have to talk about, both at big company and small company. But if you invest, we will pay. You will make money on that investment. Figure out what the licensing model is to do that, and that's the catch ball now that's got to come back. We threw the problem at you. Academics helped with you in the scaling. We have NCSA as a partner. Hardware is there. Brilliant. Now let's come back and say, now if I want to do, 40 million element calculations, and I want to do them, at 100,000 times a week, right? What's it going to cost to do that in a way that isn't 8 figures? So I just want to say thank you. And thanks NCSA and Merle for making this happen. After 5-6 years ago when we had the summit and we just felt like it all went flat, this is a watershed moment in my mind in the relationship between high-performance computing, ISVs, industry, and the academics.
Tom, you've said that exquisitely well. I want to point out a couple things that really helped make this happen. One, Blue Waters. We didn't have access to that kind of scale, and our private sector program and our own industry access onto that machine, we did some things. We broke a few rules. NSF's not in the room, but anyway, we did this because those of you in this room wanted to see that happen. We responded, and the collaboration among the PSP partners allowed us to actually get that funded and to do it. And I would say that the ISVs stepped up because you customers were in the room. I mean, you just didn't do this for grins. You did it because you actually had real customers out there. So that's the convergence again, coming together to make this happen, but it happened at a scale because of an at-scale computer. We could never have done this on iForge alone. Just shouldn't have. We've got a question in the back corner.
Yeah. Bhushan Desam from NVIDIA. I think the mantra for profitability has been the same for decades, making faster, better, and cheaper products. But that's a moving target because of added complexity. So, simulation became a way to manage this complexity rather than reduce the complexity because you don't want to shoot the value down. You want to manage the complexity. But my question is, you are actually facilitating these companies to push the boundaries. You are getting scaling on 60,000 cores, but the whole purpose of doing computing is really getting insight. So what are some specific efforts at the PSP program for companies to get this insight on these large data sets, which are, very, very difficult to move and visualize? But if you really look into the Blue Waters, there are certain researchers who are actually pushing the boundaries of visualization, looking at larger data sets on GPUs, for example, John Stone here. And are you trying to take these concepts and try to infuse this to the PSP program to really look at this as a holistic process, the process of getting insight into simulation?
I'll
Yes.
make the comment. Again, this is one of the values of trying to do these high-end simulations in a demo environment, for lack of a better term, right now. Is it proves that you can do it, right? To build a model with 100 million elements in it, oftentimes you're breaking the tools doing that. And as commented about, when you run at this scale, stuff shows up that you just normally don't see. So. It isn't just getting the simulation done, but it's having the tools to build the models, look at the results, manage the data. This is a huge part of what we're all dealing with every day in these big models is okay, you've just generated a terabyte of data. What do you do with it? You don't want to move it back to the workstation necessarily. Do you have the visualizations tools to handle it, data analytics tools in general to handle it? So I think that's all part of the process we go through and why it takes an extended team to make this happen. It's not just generating megaflops, that's for sure, or gigaflops, I guess.
Ahmed?
Just 30 seconds. On the issue of the scaling, at the very beginning of the scaling for Fluent, it came from you. One of the power users of one of the companies who are here today actually approached me and he said that I have a huge model which I need to know the scaling limit for it. It was before even we started with the answers. This brought the issue of let's check the code. So you need to drive the scaling limits, and this is for your own benefit.
I would just add from my observation that there are several layers of insights here. Some insights are in the code base itself and the way in which we went about getting this to scale. And so that is a new learning, I believe, at this kind of scale, is how to get that done. There's also insight into the science itself. So the Ahmed combustor that we had from Fluent was a non-reactive combustor. There's nothing moving. There's no dynamics in there. Nobody lit it up, and it still was a huge model. So what happens when we light that thing up and it goes reactive? Well, we don't yet know. So the insights actually come from the science, which means we need all those talents of the team at the same time. So Greg, thanks for saying that. We are going to break, or I'm going to absolutely get in trouble with our agenda here today. We'll break for lunch. We'll keep the questions going. Any of you with remaining questions, come peg these guys, but we'll be back in this room at 1 o'clock.